Good afternoon, everyone, and welcome to today's webinar. Today we will be discussing Lean Six Sigma and how to think about data. My name is Patrick Allen. I'm the Program Manager for Kent State's Center for Corporate and Professional Development's Public Open Enrollment Programs. Our center specializes in providing employee development for partnering organizations in Northeast Ohio and around the country. We offer training as public open enrollment programs delivered in Independence, Ohio, and also on-site customized programs delivered at your location. I'm joined today by Kent State facilitator Steve Skillman. I will be serving as your host, and Steve will be our presenter for today. Steve is a Lean Six Sigma Master Black Belt and the lead facilitator for Kent State's Lean Six Sigma Black Belt and Master Black Belt programs. He earned his Bachelor of Business Administration from Lake Erie College and has worked in automotive, government ballistics, and electrical insulation industries. In these industries, he has held positions in production scheduling, purchasing, shipping, and of course, quality and continuous improvement. Everyone in attendance today has been muted to avoid any background noise from any of the over 150 registered participants. We do encourage you to ask questions at any point during the hour. You can submit your questions in writing using the control panel on the right side of your screen. I will present your questions to the presenter as time permits throughout the webinar. There is a handout available. It's located on the right side of your screen under the Handouts tab. That contains some notes of what we'll be covering today, so I do encourage you to download it. We are also recording today's webinar, and you will receive an email with a link to the recording after we conclude our time together today. Without further ado, I would like to introduce Steve Skillman.
Thank you, Patrick. Today we're going to talk about our approach, everyone, to continual improvement, to operational excellence. And I'm also going to talk about a few small examples of how we can use data or statistics, analytics, to better look at our processes and understand what's going on, when to react, when not to react. So with that, our continual improvement model contains four pieces, the first of which is TOPS, which is an acronym for Team-Oriented Problem Solving. TOPS was originally developed by the Ford Motor Company in the 1980s and provided a framework for identifying, solving, and preventing recurrence of problems. As part of our continual improvement model, TOPS is where we establish an executive management level steering committee to manage the continual improvement efforts and to ensure that these efforts are properly linked to the organization's strategy. This is also where the deployment efforts begin by identifying strategic projects and assigning teams to complete those projects. The second piece is theory of constraints, which helps an organization by focusing on the system constraints or bottlenecks that slow them down, that stop them from gaining more of whatever it is that they are trying to achieve, which in our case, let's say, is more throughput. We try to reduce investment costs, try to reduce inventory and operational costs, but the main purpose is how do we improve our throughput of the organization. The third piece is lean, which was first defined by Jim Womack in his book, The Machine That Changed the World, where he described the Toyota production system. Lean provides us with methodologies and tools to identify the waste in our processes, that which the customer is unwilling to pay for, and eliminate it, thus increasing the velocity of our process. Six Sigma, the fourth piece, was originally created at Motorola, Michael Harry being one of the original architects in the 1980s. Six Sigma methodologies and tools help us to identify and reduce variation that's present in all processes, resulting in fewer defects, more capable processes, better predictable outcomes. And as a whole, the three main methodologies of theory of constraints, Lean, and Six Sigma woven together with top sort of surrounding them as to how we in an organization utilize our people effectively from the very top of the organization at the executive steering committee level all the way down through our lowest level employees. We need a little bit of all of these to be successful. So let's think about systems for a minute and processes. When we look at our organizations as a set of functional departments or silos, we run the risk of creating islands of improvement that may or may not improve the customer experience. If we look at our own organization as a system of processes or value streams, then we see our organization as our customer does. This helps to better understand the voice of the customer. We also take into account the handoffs, the white spaces, the in-between where the ball gets dropped causing problems. You see, our customer doesn't experience us as a shipping department. They don't experience us as a sales function. They don't even experience us just as a manufacturing or a service environment where they get what they asked for. They experience all of it together. And we need to start thinking of ourselves as a system as opposed to broken down in individual processes. Because a system is the functioning of all of the parts working together, not just the sum of the parts, but a product of all their interactions working to deliver the aim of the system or the aim of the business. So in order to survive, we have to change. Specifically, we have to change from a culture that promotes the status quo to one that embraces continual improvement. That means everyone in the organization, from the very top to the lowest man on the totem pole, has to be involved. Let's take management commitment. The leadership group must provide an environment where change can flourish. Management also has to walk the talk. The leadership group must be engaged, actively participate in the process and in improvement. And then our employees need to be made aware. They need to understand what's in it for me. How is this going to affect me on a day-to-day, regular basis? Management permission. The leadership group must provide the time and the resources to continually improve processes. Without the time and the ability to actually work on their own processes, improve the systems, this is all going to be for naught. Visual management. Organizations should utilize visual display, what's important, and visual control, identifying a call for action. We need to be a learning organization. Employees must be allowed to fail in order to learn. Employees have to be empowered. The employees must be taught how to solve problems and then given the authority to make decisions and stop out of control processes. We need to be better at coaching and facilitating others. The organization has to provide mentors, not just supervisors and bosses for employees. And then performance reviews. Continual improvement activities should be incorporated into performance reviews. So this way it's felt all throughout the organization from, again, top to bottom. So let's talk about the R-DMAIC-R Roadmap. In recent years, the R-DMAIC, define, measure, analyze, improve, and control rigor that Six Sigma is built on, has added two other phases. An R for recognize at the very front end, and then realize at the back end. And I'll talk about that one in just a couple minutes, but recognize. The recognize phase is really a pre-R-DMAIC or pre-project phase where we're trying to link our Lean Six Sigma to business strategy and priority. We're trying to understand opportunities that we need to make improvements and then prioritize those into which projects are going to give us the biggest bang for our buck right now, and then ultimately launch those projects. During the define phase, we've now identified a specific project, and that specific project, we're going to have to identify what's the problem or the issue that we need to resolve, who's going to be involved in doing it, What are the objectives and the goals for our team as we move along? And how are we going to know when we get there? At the very end, how are we going to know when this project is done? We should try to think ahead to those kind of things in our define phase. As we move into the measure and the analyze phase, the measure phase is really how we take a look at our current business, our current system, and collect preliminary data or map out our processes to see where we're at today, where the complexities are in our organization, and then try to identify through what we call tribal knowledge, the subject matter experts on the team, identifying key areas for us to focus on. We also try to identify inputs to our process that are delivering the outputs of the process. And usually it's the outputs that we're trying to affect. In our define phase, we identified issues that are occurring, which is why we have a project. Those are outputs. We need to try to figure out what are the key inputs to the process that are affecting and causing those outputs to be what they are, ultimately to improve them. Our analyze phase is about how do we bring statistical logic to bear. And again, we'll talk about the analyze phase a little bit more with some examples as I move along. But the statistical logic is really there to confirm what we think we knew through subject matter experts in the measure phase and let the data do the talking. Can the data back up or validate the inputs that we wanted to focus on are the right ones, or do they potentially invalidate some that we thought were important but might not have as much impact as we initially thought? And then we move down into the improve phase. The define phase, the measure phase, and the analyze phase are all there for the express purpose of delivering the most useful inputs or process improvement ideas into improve so we can ultimately make the changes that we're after. And then control phase is about how do we sustain the gains. I think of projects almost like shooting an arrow up into the sky. When you shoot an arrow into the sky, it has a lot of energy early on, like our projects do. As soon as we charter a project, there's a lot of energy and excitement in the team, and that arrow is flying up in the sky. And our hope as we hit to the peak is to get that arrow to stick into the clouds, stick up in the sky at its peak where we've analyzed and now we've ultimately put in our improvements. And the control phase is how do we sustain those gains? How do we keep the arrow up in the clouds and not falling back? So we're saying things like, well, haven't we fixed this once before? Which I'm assuming all of us have had a chance to say that once or twice. The realize phase is post-project. How do we integrate the new process, the changes into our regular day-to-day business activities? How do we ultimately realize the expected gains, benefits, dollars to the bottom line as we move forward and the project team has gone away, and the results are what we're trying to track as we move forward, maybe a month, 2 months, 6 months down the line. Recognize and realize phase, again, are fairly new to the Six Sigma methodology, and I am absolutely a proponent to add both of them into the way we think about organizing projects, from how do we select them, how do we run those particular projects through the DMAIC, and then ultimately, how do we realize the results at the back end? Next, we have to provide our employees with the tools of continual improvement. Tools to be able to find the waste and variation in our business processes. The tools to analyze our process data so that we can identify the root causes of our problems. A question that I'm frequently asked is, should we do Lean or Six Sigma first? My answer is almost always that you need to do both at some level. The role of Lean in process improvement involves an extensive examination of each step to determine if it provides value to our customer. If it doesn't provide value, the tools of Lean are used to eliminate that step or that process. Process waste is depicted in our first diagram here by the red W's. In a Lean process, we look to eliminate those wasteful activities. Now, the role of Six Sigma in process improvement is the reduction of variation. All processes contain variation. It's unavoidable. Unfortunately, if the variation becomes too great, the process creates defects, which our customer obviously is going to reject. Since we can't totally eliminate variation, we have to try to aim to control it within some acceptable limits. This diagram here illustrates the reduction in process variation by just the relative difference in the width of the curves. Also, we've aimed the process a little bit more on target, so we nestle nicely between the lower and upper spec limits that our customer expects us to meet. If we do lean without Six Sigma, we increase the velocity of the process, but since we didn't address the variation, we have a process that produces defects much faster. If we do Six Sigma without lean, we may have reduced the variation on a step or steps that should have been eliminated, and we're left with steps that add cost but not value. The result is a process that produces good parts or services but is expensive due to all of the unnecessary steps. Six Sigma, along with lean, provides the best results. The best continual improvement approach is to combine lean and Six Sigma in order to eliminate the waste and reduce the variation at the same time. This will result in a process that provides value to the customer without defects. Now, applying the theory of constraints to a process helps you to focus your efforts on the area that is limiting your throughput. Once the constraint is identified, you can apply lean and Six Sigma tactics and tools to relieve that bottleneck. Improving our process before or after the constraint without addressing the constraint does not improve the throughput to the customer, does not really help what we're making to be any more through our system. So we need to make sure that we're focusing our energies and efforts on that process in the system that is holding us back from doing more of whatever it is that we're trying to achieve. So with these three methodologies, lean, Six Sigma, theory of constraints, providing tools, tactics, methodology, cultural differences, eliminating waste and reducing variation is going to be a natural byproduct of this, which should lead to wealth and prosperity, which I'm pretty certain we all want to achieve better wealth and prosperity for our business moving forward. So let's talk a little bit about how we utilize data and how we can better leverage the data that we have. Sometimes I hear people gathering all the information they can possibly get. They want to set up a system where they can collect this and collect that, but they're not really sure what to do with it. It's to get everything you can and we'll think of how to analyze it later. I don't think that's the way that we need to approach data. I look at data collection and analysis in a different way. Now, to me, understanding of data is generally pretty inadequate out there. I feel like we go to school. We start off with grade school and high school, and we learn how to add, subtract, multiply, divide, throw in some algebra and trig and geometry and so forth, even calculus for some people. And then we move on to college and universities. They reinforce what we learned about mathematics, but not necessarily really how to think about the data that we're doing. We're taught formulas, theories, postulates, axioms, but again, I don't always feel we're taught well how to think about the data. We learn definitions, but not really how to think about data. I hate to do it, but let me take you back to a stats class. If there's anybody out there who's actually gone through a stats class, then we're usually taught to form a hypothesis. And once we've formed our hypothesis, then we have to start calculating a test statistic. And then we might even need to calculate some degrees of freedom formula. And then we have to get our textbook and we have to go into the back of the textbook into a table. compare our calculated test statistic to a critical value in the table that we entered by the way of maybe a numerator and denominator calculation. And ultimately, you determine based on that comparison of your value to the critical value whether you pass or fail the test. I generally think by the time we get through doing all those calculations and comparisons that we kind of lose sight as to what were we trying to do. What was the question we were initially trying to answer? So again, are we really taught how to think about data very well? The objective is to digest the numbers and then extract the knowledge within those numbers that we have. So one question a lot of people like to start with is, well, how much data do I need? How much is required? That question is pretty open-ended. Many people think, well, 30. I was taught 30 samples is what's needed to learn about my process. 30 is okay sometimes, not all times. Sometimes it's a lot more data. Sometimes maybe you don't even have 30. What if all you have is 8 or 10 samples? You say, well, I didn't get 30, so I guess I can't do any data analysis. Another question that's asked is, what type of data is needed? Do I need numerical data? Do I need categorical type of data? I don't think either of those questions can really be answered before you start asking your original question, which is, what do you want to know? You always need to begin by asking the question when it comes down to data analysis. Once you ask the question, then you can determine what type of data and how much is necessary to answer it. If I'm trying to identify why my equipment is down and what reasons there are for downtime, then the type of data I'm going to need is probably going to be categorical. Well, it's down for maintenance, or it's down for people taking vacation time, or it's down for changeover. But I need to collect that data. What if my question is, are my bathing suit sales seasonal? How much data is required for that, and what type of data? Well, for bathing suit sales seasonal, you're talking measured data. You're going to have sales figures. How much? Well, in order to answer the question of seasonality, you would think we would need at least a year of data, if not 2 or 3 years, to see any trends happen more than one time. So you see the question of how much data, that might not even be the right question to ask if you're looking for seasonality or trends. All of a sudden it becomes much less about how much data and more about, well, how long do I need to study the process in order to answer that question? And then within that time frame, once I figure that out, how often do I need to take samples in order to see what I need to see in seasonality? So let's talk for a minute about populations and samples. What's the difference between them? Well, what constitutes a population? A population is, by definition, is it everything that we made last night? Is that a population? Is a population everything we made last week or even last month? That's to be determined. We need to define that before we can ever figure out what our sample or sampling strategy is going to be. A population is, by your definition. What's the job of a sample? To reliably represent the population from which you gathered that, which you drew it from. And so once you've identified your population, then we can start to put together a sampling strategy that can speak for that population. Since usually it's difficult to get our hands on population information, it takes us all of our time, all of our money to try to measure everything. I've also learned that statistics in general can be misleading at times. I would venture to say that most of us out there have learned some basic statistics like mean, median, mode, range, variance. But all of these can be used to mislead. And I just wanted to show us a few kind of funny little examples as to how we can use each of these to mislead people. And then we'll get into a few simple case studies. What would my starting salary be? Well, I'll put it this way, and our average starting salary is $80,000. Yet when you take a look at the raw data, that $80,000 average doesn't seem like it really means a whole lot when you have almost everybody making, 30s, and there's one really big figure. Why should I invest with you? Well, not to brag, but my fund has a median gain of 8% per year. Yet when you actually take a look at the raw data and you see over the last number of years, there's been almost as many good years as there have been bad years, but the bad years have been 3 to 4 times as large as the good years. So a median gain of 8% really doesn't tell the whole story. How are you doing on your tests? My modal category is 70 to 80%. A mode is just the most reoccurring value, but again, here you see most of the tests are scored lower than that. Try our energy drink. It's highly correlated with performance. When you take a look at this graph, we've got professional athletes that were paid to guzzle our drink versus the rest of the population. So the amount consumed might seem to correlate to athletic performance, when in reality we've got some outliers up here that don't really paint the true story. The results are a disaster. Well, sure, they look bad, but there's a lot of variance. Don't rush to judgment. But then you see almost all of the results are not good, and we just have one kind of outlier in here that says great results. So really, the variance is large? I don't know about that. Our students come from a wide range of socioeconomic backgrounds. Are we sure about that? I mean, we can say they do because we have bars that show a wide range of incomes, but most of them look like they're maybe upper middle class. So in all of these simple little examples, I just wanted to show you how we can use statistics to paint almost any kind of story we want to. That's not how we should be using data and statistics, obviously. So let's talk about maybe how we should. How should we look at data? Let's see some summary statistics in action on an example dealing around somebody's household bill, like a gas bill. If we took a look at a traditional household gas bill and just got some summary information on it, like this. Our average is about $87 a month. The standard deviation, just a measure of dispersion of the data, is 51, and we have a minimum to maximum of $34 in one month to almost $179 on our highest month. How insightful is this information that we've gathered? Does it tell you enough to really know what's going on in your gas bill? What's it missing? What else would you want to know? I think there's a number of things on this data set that I would want to know before I could try to understand my gas bill, understand the budgeting that I would need to have. So maybe a picture will work better. Maybe a picture will tell the story. Traditional data analysis began with histograms, which can be a very insightful tool that displays our distribution and is useful in visually examining central tendency, distribution features, and the range. So here's the same gas bill information, but now in a picture. What else do we know now that we didn't before? And is this more or less helpful to us? I would venture to say it's a lot more helpful to us seeing a picture versus just seeing summary statistics. That $87 average we had before, is that really in the middle of the data? Is it what's happening the most? No. What's going on the most is somewhere in the neighborhood of probably $30 to $60 range. We knew our overall range was upwards of almost $180. Okay, so we have some of that going on. But again, a lot is down there in that $50-ish area. Box plots end up being another sort of favorite of many out there in terms of a visualization of our data. They display the min and the max of your information. The median is traditionally shown, and although the mean, we can display that as well. And then the box displays the middle 50% of your data, essentially first to third quartile for you statistics geeks out there. I could probably throw myself into that bucket. So here's the box plot of that same gas bill. Again, the middle 50% of the data is contained in that blue box. Does this help our analysis? Are we still confident in using $87 as our average gas bill per month to really tell us anything? Now we see a median of $58. Difference between the mean and the median. The mean is a calculated center. The median is a counted to center. Maybe with more skewed information, the median becomes a better indicator of real, true central tendency. And I think you saw that on the histogram before. But do either of these approaches really give us what we wanted to know about our gas bill and budgeting and what's really going on a regular basis? I would say neither the histogram or the Boxplot shows us the true nature of this data. What can we expect to see in a typical gas bill that neither graph shows? A pattern. Budgeting $87 or $58 a month doesn't reflect our actual monthly gas bill. So how should we look at the data? I think the only real answer has to be in its natural sequence of events. The previous methods treat the data as if it's randomly occurring. And I learned early on in dealing with statistics that no data has meaning apart from its context. And this data cannot be separated from the time period that relates to it. So we must look at this data in its context, which I think will give us a whole lot better picture of what's going on. Proper data techniques should always, when possible, start with data in sequence. Here's that same information for the gas bill seen in sequence. Wow. How useful is that average of $87 now? I would say not so much. Even the $58, probably not so much. The most important thing to learn about this particular data set was seen when we see the sequence of it. We can tell that there are about 4 months where we're going to be spending in the neighborhood of $150, $160. But then there's like half of the year where we're going to be spending in and around $50 a month. Very little is actually around the $87 average. And so I don't think the average is telling us a good story here. A gas bill, at least here in Northeast Ohio, where we've got winters like we do, has a big surge in the price that we pay in some months, and then we drop down for our late fall or late spring, summer, early fall months. Let me take you through another example. Shaker Steel Company. A steel manufacturer makes steel pipes for the oil and gas industry. And their 9-inch pipes were causing dimensional problems, so the quality manager grabbed data from the past 2 weeks just to take a look at it and see what he would learn. So what do you know? He started with a histogram. Like I said, kind of traditional data analysis uses histograms a lot. Anything under 8.995 and over 9.005 is deemed out of spec based on what the customer demands. So approximately we have about 7% of our data is out of spec, not meeting that criteria. So of course, investigation has to begin into what's causing it. What are some issues that could lead to that? So the main cause for steel piping diameter to be too large is usually due to the finish rolling temperature being unstable. So they spent a month analyzing finish rolling temperatures. No evidence was found showing certain temps were more or less capable. I have to ask a question. What if Shaker Steel took a different approach? What if they looked at that same data in that histogram in sequence as it occurred over those 2 weeks? Anything else maybe they could learn from it? Let's take a look at it in run order. This seems to suggest a change in the process. With proper data techniques, we now have a place to start. And when I say proper data techniques, I'm talking about when we have the ability to take our data and look at it in the sequence in which it occurred, we're able to see trends and patterns, shifts and drifts in the process. I think this data in sequence really gives Shaker Steel a place to start thinking about their analysis better. So in sticking with this idea of data in run order, I want to introduce the control chart to you. Control chart is a type of run order chart where data is organized in its sequence and variation in the process is assessed. And a process can be characterized in two ways: in control or out of control. Let's understand what those two terms mean a little bit better. In control means the variation in your samples can be attributed to random chance, just the natural, normal, inherent variation in your process. And an in-control process is said to be stable or predictable. Out of control means the variation in the samples cannot be attributed to random chance, and therefore that process is unstable, it's unpredictable. If it's not attributed to random chance, then that means there has to be some causal agent, something that actually made that event occur. You know, I like to use an example like driving a car. If it takes me 30 minutes to get to work on a regular basis, obviously there's going to be some variation around there. If I get to work in 28 minutes some days, 32, 33 minutes in other days, that's normal inherent variation of a very in-control process, predictable. An out-of-control event or a special cause event that is not just random is I got a flat tire on my way to work and it took me 90 minutes instead of 30 minutes to get to work. That's not random. There's a special event that we can pinpoint to that particular event and data. So let's take a look at a control chart for our Shaker Steel data. When you plug those 2 weeks worth of data onto a control chart, we can see now, based on the red lines representing behavior limits or control limits, and the green line in the middle representing the average, that we've now identified 2 out-of-control points, which generally tells us something has changed in our process. Something's different. Investigation should occur based on those 2 out-of-control points. But when did the change occur? Do we just investigate those 2 points when they occurred? Or do we look at the process as a whole and say, it seems like there was a change that happened somewhere in and around the middle of the data that might account for we all of a sudden seem to have a couple high points? So upon further review, a change in raw material suppliers was found beginning at point number 79. Clearly an upward shift looks to have occurred from then onward. So can we maybe throw out this idea of the rolling temperatures being a cause, because we didn't find any relationship there, and now we're back to it's just a raw material supply chain change, where our first supplier seems to have been doing something very different than our second supplier in terms of our process internally. When you take a look at this particular graph, the process using the original material appears nestled neatly between the specification limits noted in green. I have to apologize. The green lines say a UCL and LCL. Those really should be upper spec limits and lower spec limits for the green dashed lines. But if you apply the spec limits to these 2 different raw material suppliers, our first supplier within our process, we've been able to maintain within the specification limits. The new suppliers material we've moved to, we have not been able to maintain that, hence out of spec or out of desired parts for our customer. So how would you answer this question? The boss inquires, why scrap up 2% from September to October? Answer, what was so special about October? Why are we looking at October as if it was a special event or special cause? How do you know October really was a signal and not just normal random variation in our process? Reality is you can't possibly know without sufficient data to generate a control chart. A run chart could help, but a control chart allows you to separate out the natural, normal variation in your process from that special variation. So let's take a look at scrap percent from the casting process here, where we have about a 2% change. The boss is assuming this change from 1 month, September to October, is a signal that something different has occurred. And we've got almost 17% scrap in October versus almost 15% in September. But is that change really a signal? Does it tell us something really did happen in our process that we need to investigate? And then another question is the graph misleading? Has anybody ever seen or maybe even used a graph like this, where if you look at the axis for the scrap percent, the way that this graph was set up actually looks like October is almost twice as large a scrap as September, when in reality there's only about a 13% increase in scrap numbers from 14.8% to 16.8%. Very misleading graph, on top of the fact that we don't know if the change is actually a signal that our process is different. So let's take a look at it in run order, in sequence, as I've been trying to get across is so important. That 2% increase in October, those last two data points, September being the second to last, October being the very last, we can't attribute that change to any specific cause. Random chance fluctuations in the process account for that from the month-to-month changes on our scrap numbers. We need to start getting to looking at our data in such a way where we can plot it in sequence, because without that, and without putting them on a chart like this control chart here, where we can identify the natural normal variation of the process fluctuates some up and down from any extraordinary occurrences, special causes, then we really can't make any good calls. So using data is frequently, we want to use data to detect signals that require action, but far too often action is taken when no signal exists, and conversely from that, frequently action isn't taken when it should be. Well, how do we distinguish between a signal and normal process variation? Well, there's the question of the day. When is action required? Only when a signal is detected. And how do we distinguish between normal variation and a signal? A control chart. That's its purpose. Data points occurring between the control limits, I keep calling them behavior limits, are generally not signals in your process. Exception being when data is time ordered and you might be able to see trends or unusual patterns or shifts in your process, then it's very possible that they could be happening within your control limits or behavior limits and still truly be special causes. So until you get your data onto a control chart, a run chart of some sort, you really don't know enough yet. Before decisions are taken resulting from the analysis, it's essential to separate common cause from special cause. It's best done on a control chart. Remedial actions regarding common cause variation are very different than actions one might take to remedy special causes. Again, I just have to take you back to the drive time example. If I don't like the variation around the 30-minute drive time and I want to improve that, what kind of actions would I need to take to improve the drive time? Take a different route to work, leave at a different point in time, maybe even move closer to work. But are those the same actions that it would take to improve my 90-minute drive time when I got a flat tire? The answer is clearly no. To improve that, I need to work on maybe how I fix a flat tire or run flat tires. But the actions taken for common cause and special cause are clearly different. And the control chart allows us to separate those out so we can decide how our improvement efforts are going to go about occurring. We need to resist being held accountable for fluctuations in data unrelated to special causes. Common cause reflects the natural signature of our process, and if that's not acceptable to others, then we need to make systemic changes. Workers generally labor within the systems that they have little influence over. It's management or the company that owns the system and therefore is responsible for those systemic changes. like the scrap percent that increased from September to October, that was part of the natural occurring variation in the system. If we don't like the scrap being that high, it's not due to a special cause. It very well could just be a systemic issue that we need to look at everything occurring within those limits and say, why is our scrap percentage typically between 12% and 17, 18% that our control chart showed us? So with that, I just wanted to give us some things to think about today as to how we can use data, statistics, analytics, if you will, to better understand processes and also see that it doesn't have to be a scary proposition to use math and use statistical software. There really can be some simple techniques that allow us to identify variation, where it's occurring, when it's occurring, and how to better really improve our processes and monitor them on a regular basis. With that.
Thanks, Steve. We did have some questions come in, and we'll try to get through as many as we can in the interest of time. So the first one, what are the most common mistakes or challenges involved in implementing a Lean Six Sigma initiative?
Thanks for the question, Patrick. To start with, Lean or Six Sigma must never really be seen as a tool for headcount reduction or mindless cost cutting. This fundamentally misses the purpose of Lean, which is to create value through eliminating waste. As companies improve their processes, they should be able to reallocate those productive resources to new value-creating work. Another important attitude to avoid from the beginning is the impulse to implement individual Lean or even Six Sigma tools without seeking to understand the system in which they fit. I know it's kind of hard to avoid at times since many tools like, let's say 5S, will deliver immediate payoffs. But ultimately, all of our workers must understand some of the why behind the tools or the value is going to be lost. Beginners should also limit the scope of their initial projects so they better ensure success. Be sure that they have a leader or coach, mentor with deep knowledge and a Gemba attitude. What I mean by that is one that always bases their thinking on a close observation of the work itself and really never relax in any of their efforts.
Okay, thanks, Steve. Another question that came in actually asks about math skills. They said, how good do my math skills need to be to learn and use Six Sigma?
That is a very common question asked for people that get scared a little bit of Six Sigma, is the statistics part of it, which is part of why I want to talk today and give some examples on how we can use data to better analyze our processes. But nobody needs to be a math genius out there. Some Six Sigma components require statistics so that improvement in quality can be measured. However, very few Six Sigma tools involve a lot more than complex or anything more than complex basic statistics, if you will. Many of the results are expressed in terms of raw numbers or percentages.
Another question involves what industries have been used, has Lean Six Sigma been used in? It says they've heard the majority of it is just for manufacturing. So what's your take on that, Steve?
I think this scares a lot of people away from Lean and Six Sigma because they were methodologies born out of manufacturing. You can't take away that history. But the reality is Lean and Six Sigma over the last 30 years, people have learned that this isn't just for manufacturing operations. In fact, healthcare organizations have been maybe one of the biggest, if not the biggest, proponent of Lean and Six Sigma activities since, I'd say, the early 2000s. Government, boy, could they use it, but government organizations, we're seeing more and more, even if it's just at local and state government levels, are using some Lean and Six Sigma methodologies. And then we have to also understand that for those of us that are coming out of a manufacturing business organization or mindset, most of what we do within our own businesses really isn't just turning raw material into widgets and gadangis. I would venture to say 60 to 70% of any manufacturing organization are service and transactional type of operations, where we can look to improve our hiring processes. We can look to improve our supply chain and logistics operations. We can look at our sales and marketing strategies better. We can identify engineering, customer service support. Lean and Six Sigma is absolutely not just for manufacturing, despite it starting there. Many organizations have come along and understand that these can very easily and quickly adapt right into their environment today.
Okay, Steve, I think we have time for maybe one more. Let's see. What is the best way to identify projects for Lean Six Sigma?
Well, the good thing about Lean and Six Sigma is that there's really a whole suite of tools and ways to identify projects. One could be an enterprise level look at a value stream map, which we can use to highlight projects in context to the whole company. We can also look at a cost of quality analysis, which usually identifies a host of projects to work on. And techniques like voice of customer and Kano modeling will illuminate the customer's perspective of what the important projects are that we should be looking at. Undoubtedly, though, the best way to identify projects is through a strategic deployment process, which takes into account the external and internal customer perspective and aligns our projects and goals to strategic objectives. We need to find ways to connect what we do at the strategic level, steering the ship, up at the executive level, what I would call the steering committee level, all the way down to our tactical deployment, which is where the Lean and Six Sigma and theory of constraints type of activities occur. We need to connect all that. So we look at that from a very top level on down to identify the best projects that are going to advance, our aim.
Okay, great. I think that's really about all the time we have today for questions. So I do want to thank everybody for joining us today. If you would like to learn more about today's topic, we encourage you to register for our next Lean Six Sigma Black Belt program, which begins March 11th at the Educational Service Center of Northeast Ohio, which is located in Independence, or the Green Belt program, which begins on April 1st and will be held at the START campus in North Canton. You can see the registration link on your screen. We can also tailor any of our programs and deliver them on site for your team. You can join our extensive list of clients, which you can see on the screen here, and bring Kent State to your organization. You can contact us at 330-672-3416 or at your training partner at kent.edu. We also encourage you to register for our next webinar, which will be a discussion about interpersonal communication skills with Kent State facilitator Deborah Easton on December 18th. For those attending live, you will be asked to complete a short survey. Please complete this survey so that we can be assured that we are bringing you the most usable and relevant content possible. You will also receive an email with a link to view a recording of today's webinar. On behalf of Kent State Center for Corporate and Professional Development and our facilitator, thank you for joining us today and have a great rest of your day.